In this video, I will be going over the homework exercises from section 3.1 in WebWork. In section 3.1, we studied properties of polynomial functions. In problem 1, we're looking at the end behavior of the following function. To determine the end behavior, we need to find the leading term in the first part. The leading term is the term that has the highest degree. So in this case, 19x to the 14. That would be the term with the highest degree. So the leading term is 19x to the 14. The degree is the highest power of the variable, which is 14. And the leading coefficient is the number in front of the x to the 14th power, so it's 19. Using this leading term, 19x to the 14, we know that when a polynomial has even degree, the tails will point in the same direction. So it's either going to be end behavior A or D. The leading coefficient is a positive number, so this leads to this end behavior A, where both tails to the left and to the right will be both pointing up. On problem 2, we have to determine the end behavior again. So now this function is written in standard form in decreasing powers of x, so the leading term is actually the first term, 7x to the 11th. Again, this is the term that has the highest exponent. The degree is 11, the leading coefficient is 7. So now with an odd degree polynomial, the tails to the left and the right will point in opposite directions. So this is end behavior B or C. Since we have a positive leading coefficient and an odd degree, this will be option C. And the end behavior can also be confirmed by graphing this polynomial function on a graphing calculator or other graphing utilities. For problem 3, we have to write the end behavior in terms of infinity or negative infinity. So the first part says p of x approaches blank if x approaches negative infinity. So recall this means x going to negative infinity means way out to the left on the graph. X going to positive infinity means way out to the right on the graph. So every polynomial function will either go down to negative infinity or up to positive infinity, way out to the tails, to the right and to the left. So let's look at a sketch of this graph. I used the Desmos.com to graph this function. We zoom out, we see that this is a cubic polynomial, degree 3 polynomial, with a positive leading coefficient. So the function is going down to negative infinity to the left and up to positive infinity to the right. On this problem, the instructions say to enter your answer as negative infinity or infinity. So you actually have to type out the whole word. So x approaches negative infinity, way out to the left, we saw that the function is going to negative infinity. It's going down. And to the right, as x goes to positive infinity, the function is going up, so we say p of x is approaching infinity. In the past, we've entered INF or negative INF, but in this case, you actually have to type out the whole word. Let's go to the next problem. In problem 4, we have to state the degree, the number of terms, and describe the end behavior. This polynomial function is written in factored form. So to find the number of terms and the degree and the end behavior, we're going to multiply out this whole expression. Okay, so here is the expression for problem number 4, and I'm going to multiply out all of these terms. First, we multiply out terms 2 at a time. So I'm going to multiply out x times minus 4x and get minus 4x squared. X times 6 is plus 6x. Negative 5 times negative 4x is plus 20x. Negative 5 times 6 is negative 30. So the first two terms multiply out to this expression. I'm going to collect like terms before I multiply out the third factor. So I have a minus 4x squared, 6x plus 20x is plus 26x, minus 30. And now when I multiply out this expression, I'm going to multiply out each term by term. So minus 4x squared times 4 is minus 16x squared. Minus 4 times minus x, it gives me a positive 4x cubed. 26x times 4 is 104x. 26x times minus x is minus 26x squared. Minus 30 times 4 is minus 120. Minus 30 times minus x is positive 30x. So to collect all these like terms, we have the leading term is going to be 4x cubed. I have minus 16x squared and another minus 26x squared. So that gives me a total of minus 42x squared. I have 104x plus 30x. This gives 134x. And then the constant term would be minus 120. So from this expression, we can see now that there are four terms, 4x cubed minus 42x squared plus 134x and minus 120. And we're also asked to find the end behavior. Well, to determine the end behavior, we need the leading term, 4x cubed. This has a positive leading coefficient and an odd degree. This gives us an end behavior that looks like this, down to the left and up to the right. So we saw that the leading term was 4x cubed. This gives us a degree of 3. When we multiply out, we had 4 terms, and we saw that the function goes up to the right, so we say y goes to infinity as x goes to infinity. That means way out to the right, the graph is going up. And as x goes way out to the left, so minus infinity, the graph is going down to negative infinity. In this case, we can just type in inf or inf or minus inf for our answers. Let's go on to number 5 now. In this problem, we're asked to find the smallest degree polynomial which could have the following graph. Let's examine this graph more carefully. We notice that there are 3 turning points on this graph. A turning point is when the graph goes from decreasing to increasing, or from increasing to decreasing. So basically, the bottom of the valleys or the top of these hills, those are turning points. We know that a polynomial of degree n will have at most n minus 1 turning points. So we see 3 turning points, so this tells us that the degree has to be at least 4. The degree always has to be at least 1 more than the number of turning points. So we see that the degree has to be at least 4 from the turning points. We also know about x-intercepts that a graph will cross the x-axis at most n times if the degree is n. So we see 1, 2, 3, 4 x-intercepts. This also leads to us concluding that this polynomial must be at least degree 4. Now, we also want to look at the end behavior. The graph points up to the left and up to the right. So this gives an even degree, and further it has a positive leading coefficient, but we know it has to have an even degree. So this also leads us to believe that the polynomial function has to be at least degree 4. If the tails were pointing in opposite directions, we would know it had to be an odd degree. So we can, from this graph, we see that from the turning points and from the x-intercepts, and even the end behavior, we see that the minimum degree must be 4. So the smallest possible degree is 4. And we see from the message here, the degree has to be at least 1 more than the number of local extrema. So that's the local mins or local maximums, the turning points. Now for number 6, we have a polynomial function in factored form again, and we are asked to find the x-intercepts and also determine the end behavior again. So here's the expression for f of x. Now to find the x-intercepts in part A, we need to solve f of x equals 0. So that is, we need to set the function equal to 0 and solve for the x values that give an output of 0. So it's very nice to have this in factored form, because when we set 2 minus x times x plus 4 times 3x plus 3, the quantity squared, equal to 0, we know that from the zero product property, the only way a product could equal 0 is if one or more of the factors equals 0. So we can set each individual factor equal to 0. So 2 minus x equals 0, or x plus 4 equals 0, or 3x plus 3 equals 0. Now notice that there's an exponent of 2 here, so we actually have two factors of 3x plus 3, but I'm not going to set each one equal to 0 and solve. That would just be redundant. So we just need to set 1 equal to 0. Now solving each one of these three linear equations gives us an x-intercept. So if I add x to both sides, I get 2 equals x, so x equals 2 is 1 x-intercept. Subtracting 4 from both sides, I get x equals negative 4 as an x-intercept. Subtracting 3 and then dividing by 3 on both sides gives us x equals negative 1. So those are the three x-intercepts. And part B, we're asked to find the end behavior of this function. Now, in order to find the end behavior, we need to determine the leading coefficient, or the leading term. We could multiply out this whole expression like we did in problem number 4, but a faster way is to note that the leading term will come from multiplying all the terms with an x in it. So if we multiply the minus x times the x times the 3x, now remember there's two factors of 3x here. So the leading term is going to equal negative x times 3x times 3x. That's what would happen if you multiply out all four of these factors. So x times x times x times x gives us x to the fourth, and the coefficients minus 1 times 3 times 3 gives us a minus 9 x to the fourth. From this leading term, we see that the even degree means the tails will point in the same direction. A negative leading coefficient tells us that both tails are pointing down. So the end behavior would look like this: down to the left and down to the right. So we say that as x goes to negative infinity to the left, the function f of x is also approaching negative infinity. It means it's going down. And as x approaches infinity to the right, the graph is going down, so we say f of x approaches negative infinity. Now back to web work. We saw that the x-intercepts were at 2, negative 4, and negative 1. We need to separate these with a comma: 2, negative 4, and negative 1. And as x goes to infinity, that means way to the right, f of x is going down to negative infinity. And as x goes to negative infinity, way out to the left, f of x is going to negative infinity. Now number 7 is using the same function. Number 7, we have the same polynomial function, but we're asked to find the degree, the leading coefficient, and the constant coefficient. So this is the function in number 7, and instead of multiplying out each term, each one of these four terms, we can find the leading term by multiplying all the terms with x, and this gives us a leading term of minus 9x to the fourth. Well, we can do the same trick with the constant term. The constant term of this polynomial will occur by multiplying all the constant terms of the four factors together. So we have the constant term is going to be 2 times 4 times 3 times 3. Now notice that they're all of the constant terms are positive, so you'd have to include any negatives with the terms. So 2 times 4 is 8, 3 times 3 is 9, 8 times 9 is 72. So the leading term is minus 9x to the fourth. So we see the degree is 4 and the leading coefficient is negative 9, and the constant term is 72. So So we had a degree of 4, because it's negative 9x to the fourth. The leading coefficient is negative 9, and the constant term is 72. So this finishes our 3.1 homework problems.